things about liquid solids and phase changes. We'll focus on a portion of the learning objectives in the middle here. We're going to think about different phase changes and explain some relative enthalpy changes. Some of this may seem straightforward, but it's worth discussing these things because sometimes we get lost. And so a phase change is what we call a change of state. We're only changing the physical state of a substance, but not chemically changing the substance. And there's a variety of changes where we go from one phase to the next. I like to often refer to just solid to liquid to gas, the way we note things in our chemical equations, and we need to think about what transitions correspond to each of these. Solid to liquid is the first one. We call that fusion. And the reverse of that is going the opposite direction, liquid to solid. So that would be called freezing. Sounds like hopefully logical. The second change from liquid to gas we call vaporization. So that would be change number 3. And the reverse of that is gas to liquid. It's called condensation. And so reversing that process is like rain falling out of the air. Literally, it is condensation, or the moisture accumulating on your glass on a cold glass in the summertime. The last one is sometimes less obvious because we don't see these examples as often. Sublimation is going from solid to gas, so going all the way from solid to gas. That would be that process that we know with the arrow there. And the reverse of that, which is not always described, is called deposition, gas to solid. And so that would be the reverse of the sublimation process corresponding to that arrow. All right, what do we do with these things, or how do we understand them? We need to understand that there's heat changes. It takes heat to get things from solid to liquid. That makes sense when you think about it. And so it is an endothermic change. We have to add heat to melt something or to vaporize it. Perhaps we remember talking about this in an earlier chapter. But the reverse is also true. If you're going to condense the gas, it is exothermic. And the freezing of liquid water to make it solid, again, that is also exothermic. You have to lose energy to do that. And so you can think in terms of those sorts of ideas, whether you add or lose heat. It makes some kind of sense, hopefully. But there's always going to be enthalpies for each of those changes. Sublimation is likely is analogous as well. That's going to be an endothermic change, and deposition is going to be exothermic. So we will have enthalpy changes for each of those kinds of processes that we can describe. On the right here is something called entropy. That's a topic for another course. We won't get to that one here. All right, so if you looked at a heating curve, this is called a curve, which is pretty funny because there's no curved edges in them at all. We're going to see a pure substance that's being heated from a very cold temperature at the bottom, at the left, below 20, minus 20, up to 0. There's more heat added, and it proceeds to go from minus 20, up to 0. And then at 0, the heat is adding, but the temperature doesn't change as we go from here to V to W. You add more heat after W, and the temperature goes from 0 now up to 100. And the temperature climbs steadily as the heat is added until you get to the next point up at the top here, where X goes to Y without the temperature changing while heat is being added. And you're trying to figure out what's going on with this with this graph or this chart. Well, if you take a look here, we're going from solid to liquid at 0 Celsius, and because these are Celsius temperatures, and you're going from liquid to gas at 100. Well, that pretty well tells you that this must be good old water. So how do we understand these different parts of this graph? It's called a heating curve, and here's one that has more details to it. So you can think about how much heat is added in kilojoules per mole with actual numbers here in a different fashion instead of a hypothetical one. And so the first part of the graph, where we have a level spot, the plateau at 0 Celsius, is where you have to add heat until all the ice is melted to the liquid. And the second plateau is the boiling point at 100, where all of the liquid has to turn into gas. And so heat is added without the temperature changing until all of the liquid is turned into gas. So there are heats of vaporization and heats of fusion represented here, and the length of each of those lines is representative of those heat changes. So heat of fusion is used here, and the heat of vaporization is used here. And so the part in between where we're heating liquid water, well, that would be specific heat of water liquid. And down here is the specific heat for ice. And the one at the top would be a specific heat for water vapor. So water as a gas. That's easier than writing water vapor, right? OK, so that's how you can interpret a graph like this. But more than that, what else do? We often have some calculations involved that aren't so incredibly complex, but there are a lot of steps. So we describe these things in terms of what they mean. Enthalpy of fusion, the amount of energy required to overcome the intermolecular forces to convert a solid to a liquid. And enthalpy of vaporization is what it sounds like, converting a liquid to a gas, the energy needed for each of those phase changes. That makes a little bit of sense. There are some charts that give you values of heats of fusion or vaporization for lots of compounds, of which most of these you have no reason to memorize them. The main thing to notice is which ones are larger. So for a given compound, it's pretty conspicuous that if you compare fusion and vaporization, vaporization is always larger. And which substances have the highest values of heats of vaporization? Well, take a look at that last column over there. And pretty clearly, mercury is way up there. Not that you want to run into vaporizing mercury, it wouldn't be a good idea. But also water is up there, and interesting, ethanol is somewhat high too. But water is high relative to some of these other things. Helium as a gas is very low. So when you need them, you'd look them up. You don't need to know them memorized. OK, I'm going to skip that example for today because it was used in class. Which of these following statements is false? So what does the heat of vaporization have to do with here? And what makes things true or false? Does water have a high heat of vaporization because of strong intermolecular forces? Well, for water, what are they? They're hydrogen bonds, and those are pretty strong. So that sounds true. And the heat of vaporization of water is not as great as that of mercury. Well, if you go back to the diagram, apparently that is also true, the chart. The intermolecular force is responsible for water being mainly liquid between 273 and 373 Kelvin, in other words, between freezing and boiling. Are hydrogen bonding? Yep. And dispersion forces? Yep. Dipole is also included, so those are true. So the last one better be false. So dodecane, which you don't really know much about, but you can tell that it's comprised of merely carbon and hydrogen, has a boiling point that's stated here, and that the statement to evaluate says it must have stronger hydrogen bonds than water. Well, that cannot be true, because any compound that has hydrogen bonds must have oxygen with a hydrogen attached, nitrogen with a hydrogen attached, or fluorine with hydrogen attached. None of those are present in a compound with only carbon and hydrogen, so that cannot be true. So this is false. Has a higher boiling point for other reasons, namely London forces. OK. The other thing we'll need to learn how to relate to in these heats of conversion, enthalpies of phase changes, is how you do some calculations. How much heat then is required to convert a certain amount of ice to steam at a given temperature? And so ice is clearly going to be below 0, and the steam is going to be above 100. In order to do that, here's some values you'll need to have. First of all, there are different specific heats. There's one for ice. There's one for steam, which are unfamiliar to us, but the one for water is one we have seen before. They're always joules per gram degree Celsius for the typical units we see. Then in addition to that, you need some heats of vaporization and heats of fusion. So those each will have their place in this calculation. This problem requires lots of steps, so we have to think carefully about what's going to happen as you take ice at -5 Celsius to steam above 100. So to begin with, you heat the ice. And if you have a given number of grams, here you go, 850 grams. Multiply that times the specific heat of ice right here. That would be the value number 1 in our list of choices here. And multiply that times the temperature change. In other words, this is just Q equals delta T times the specific heat times the mass. Same idea, slightly different order, and you get a number. It's a number of joules, but probably in the end we'll look for kilojoules, so let's report it that way. Secondly, you need to melt the ice. So what is going to be used there? This would be a heat of fusion, so let's use this one for step number 2. So we take our 850 grams, and this one is per mole. Oh. So pay attention. You'll take your grams, and you'll relate it to the molar mass. Then the grams will cancel when you do that. And then it's just kilojoules per mole, and the moles cancel, and your answer is, again, in kilojoules. Second step. Now that you have ice melted, it is really only at 0 because the phase change happens at 0, and it doesn't get any warmer until the phase change is complete. So the next thing you have to do is heat the water. And apparently going to get from 0 to 100, you're going to have to get it to boiling. So the temperature change here, this is the same specific heat kind of equation. And so 850 grams times the specific heat of water, which is value number 3 up here at the top, times 100 degrees Celsius. So the Celsius cancels, the grams cancel. Your answer is lots of joules, so we'll restate it in kilojoules. Just a mathematics exercise on your calculator. Oh boy, so we're not done yet because we're aiming to get to 120 Celsius. So we'll take that 850 grams and we're going to have to boil the water. Oh, boiling the water. What does that take? It takes the heat of vaporization. So vaporization is this value here. And to do that, you just pay attention to your units and you'll be okay. It really helps. You take your grams and use the molar mass again. And the grams are canceled because your units up here are per mole. And so once you have moles, you can use the value of the heat of vaporization, which is just another number to put in the calculation at this point, and another answer in kilojoules. So then the last step then is to heat the steam. And so heating the steam is going to be the last of these constants provided. This is step number 5, or constant number 5 over here. And so step number 5 in this crazy long thing is to take that 850 grams using the specific heat of steam, which is provided. The grams now cancel, multiply times the temperature change because we're headed up to 120 Celsius. And so the Celsius cancels, and the answer is in joules, but converted to kilojoules. So in order to do this entire process, you have to add all of these things. So you add this one plus this one and the next 4. All those 5 pieces together to get an answer. Wow, there's a lot of steps to that. Of course, you have to be very careful with your math to get them right. Surprise. Let's do another example that feels very similar to that one to see if you can make sense of it. This time we're going to take ice at -10, and we're going to heat it up to 30 Celsius. Ready, set, go. And provided here we have, again, the molar heat capacity. Oh, it's a slightly different one. Molar heat capacity, so it's per mole, for ice, for water, and also a heat of fusion, which, of course, would be needed here. So first of all, let's lay it all out. We'll have to start with our 5 grams, and in order to use moles here, we have to find out the number of moles of ice. So take your 5 grams and use a molar mass, and we have a number of moles. Got it? Of course, that should be less than a mole if you've got 18 grams per mole. That looks right. Secondly, we're going to heat the ice, and this is a per mole value for what? What are we doing? We're heating the ice, so we're looking at the heat capacity of ice. That's this value right here, the 36.6. Not that you memorize things, you always look them up. And we're going to multiply these things out so that the moles cancel, and joules per Kelvin. And where this is Kelvin in this case, well, it could just as well be Celsius, because the difference in temperature looks the same in Kelvin or Celsius. And you get an answer. And we're going to go to kilojoules because that's pretty common in these units. So 100 joules becomes 0.1 kilojoules. Next step, melting the ice. What does that require? Let's see what other numbers up here that we can use. So melting, that would be the heat of fusion. So the heat of fusion is used for the next step. And we're going to use how much? Well, it's the ice that's the mass of the ice that's provided times its molar mass. And again, that allows the grams to cancel. But we're using kilojoules per mole, and so that's why we had to get to moles. The moles will cancel, and you punch it into your calculator because no one wouldn't want to do that. And you can do this one as kilojoules or joules. Perhaps we're probably going to stick with, and we can do these either way. We'll find out which one we choose at the bottom down here. Then the last step is to heat the water. heating the water. Well, that would require, the one that we haven't used yet is a molar heat capacity for water. It's a number you don't recognize because you don't always use that variation, but sometimes we do. And so you're going to take your number of moles times the molar heat capacity shown up there, 75.3, so the moles cancel. The K here is Kelvin, but the temperature change in Celsius is going to be the same as it is in Kelvin, so that's not a problem. And again, we'll punch in the values and we'll get an answer. So either you add them all up to get the overall heat, and it comes out to be joules, or you relate it instead to kilojoules. If it's 239,000 and a half joules, then it's 2.395 kilojoules. Wow, right? 239 and a half kilojoules. So make sure you get those things right. 239, that's decimals in the wrong spot. Decimals in the wrong spot. 239 and a half kilojoules, or otherwise 2.3 or 240 kilojoules. All right, hope those feels helpful to you. I'm sorry for that error in the calculation here. That will conclude this section about phase changes and how we do calculations for them using heats of fusion and heats of vaporization and their heat capacities. Good luck as you study these topics. Ask lots of questions, and I'll see you in class.